Section 7.3, Part 2, Volumes of Solids of Revolution, specifically disks and washers. So, now not only are we going to be creating solids, we're creating them by rotating them either across the x-axis or across the y-axis or across some line that we've created. So these two methods, a disk and a washer. So a disk is like a Frisbee disk, right? So it's a solid, right? No holes, just one large disk. A washer, on the other hand, is similar to a donut. So it's got this outer solid and then an inner circle, an inner hole. Okay, so we're looking at disks and washers and how they're created when we revolve them over an axis. So for problem number 1, we want to find the volume of the solid obtained by rotating the region bounded by y equals x squared in the x-axis and the line x equals 2 about the x-axis. So we are looking at this area here. So we're taking this area and we're going to rotate it so that it comes around. And even as I draw this, you notice that it becomes sort of disc-shaped. Right? So every part of it will be revolved around the x-axis, and that's how we get this shape here. Okay. So because we're revolving it around the x-axis, right, halfway through the disk would be our x-axis. So this space up here is our big R, or our big radius. And we know that this from x to this upper line here is x squared. Okay, and this space here is just going to be our change of x, or our dx. Okay, so to find the area of our actual disk, because it is going to look like a circle, right? Our disk is perpendicular to the x-axis, so x is the variable. So then to find the area of our disk, area of a circle is just pi r squared, and we're using a big R. So then the area of our disk is going to be pi x squared, which is just pi x to the 4th. So then again, to find volume, right, we integrate. And since we're in terms of x, we're looking for the x value, so we're starting at 0, going to 2. So from 0 to 2 of our area of x dx. So we're going to integrate from 0 to 2 of pi x to the 4th dx, which is equal to pi x to the 5th over 5 from 0 to 2, which is equal to 32 pi over 5. So now we're looking at a very similar problem, but now we're rotating the region around the y-axis. So now, because this is going to be perpendicular to the y-axis, y is going to be our variable. So we want to find the volume of the solid obtained by rotating the region in the first quadrant bounded by y equals x squared, y-axis, and the line y equals 4 about the y-axis. So because y needs to be our variable, we have y equals x squared. So we need to change that so that it's x equals. So we'll square root both sides, so x is equal to the square root of y. So we rewrite this as square root of y equals x. So now, if I look at my disk, halfway through my disk, right, if I take this space and rotate it around, halfway through my disk, it's going to be my y-axis. So if I'm only looking for this space, that is just square root of y. And that'll be my big R. And then this space will be my change in y. So my area for my disk is going to be equal to pi big R squared, which is equal to pi square root of y squared, which is just pi y. So then to find my volume, I'll take the integral from, since we're in terms of y, we're starting at 0, going to 4, so 0 to 4 of my area in terms of y dy. So v is equal to the integral from 0 to 4 of pi y dy, which is equal to pi y squared over 2 from 0 to 4. So v is equal to 8 pi. Okay, problem number 3, I want you to actually try on your own. You want to find the volume of the solid obtained by rotating the region bounded by y equals square root of sine x and the x-axis on the interval from 0 to pi about the x-axis. Okay, so you're finding the disk perpendicular to the x-axis, and x is the variable. So find your big R and go from there. Now problem number 4 is when we start getting into washers. So we want to find the volume of the solid obtained by rotating the region in the first quadrant bounded by y equals x squared and the x-axis and the line x equals 2. And we want to rotate that about the y-axis. Okay, so we have a washer perpendicular to the y-axis. So y is my variable. So we're going to take y equals x squared, and we're going to change it so that it's no longer y equals, but x equals. So x equals square root of y. So now, again, like I said in the beginning of the video, a washer is like a donut. It's got an outside solid, and then the inside is space. So if we look at this problem, this shaded area is the only piece getting rotated around. Okay, so when I rotate around, all of this space in here is empty. It's all empty space. This is the only space that's rotating around, so it'll end up sort of looking like a donut. So to take into account that there is such empty space on the inside, our actual area of a washer is equal to pi big R squared minus pi little r squared. Okay, so the big R will be the whole thing. The little r will be just that inside missing piece. So if we look at this washer, our big R is the whole space from the y-axis to this line, which is true. So our big R is equal to 2. And our little r is just from the y-axis to our inside line, which was square root of y. And then this space is just delta y, our change in y. So we have the area of our washer is equal to pi 2 squared minus pi root y squared. So the area of our washer is equal to 4 pi minus pi y. And now if we want to actually find the volume, which is what this is asking us to do, we need to find our limits of integration. Okay, so these two lines intersect here at 2, 4. And we started at 0, 0. So our limits of integration, since we're in terms of y, are going to be from 0 to 4, and we'll plug in the area in terms of y, dy. So v is equal to from 0 to 4, the integral of 4 pi minus pi y dy, which is equal to 4 pi y minus pi y squared over 2 from 0 to 4, which equals 8 pi. Okay, so this next problem, problem number 5, is another washer problem, but now you're rotating over the x-axis. I want you all to try problem number 5 on your own. Okay, my hint is that the top function is y equals root x, and the bottom function is y equals x squared. Okay, so just remember you're finding your big R and your little r, so that you can find the area of your washer. Okay. Now, problem number 6 is a little bit different. We're still finding volume of a washer, and now we're rotating the region bounded by y equals x squared in the x-axis, and the line x equals 2, and the line y equals negative 3. So now for this problem, the difference is this is the space that we're kind of rotating, but the entire space that's being rotated is this space here. Okay, so this is going to cause that empty space right in here. This little space in here is going to cause that opening. Okay, so we're still looking for our big R, we're still looking for our little r. Now, in this case, our big R, since we're rotating over this line, y equals negative 3, our big R is actually this whole space from y equals x squared. So the big R is the whole space from x squared plus this little space of 3. Right, that's going to be our big R. Alright, our little r is just that little open space of 3. So then, because our washer is perpendicular to the x-axis, we don't have to change anything because x is the variable. So big R is equal to x squared plus 3. Little r is equal to 3. So our area of our washer is equal to pi big R squared minus pi little r squared. So we have pi x squared plus 3 squared minus pi 3 squared. So our volume is going to be the integral from 0 to 2, because this line said it was x equals 2, of our area in terms of x dx. So we have from 0 to 2 the integral of pi x squared plus 3 squared minus 9 pi dx. Right, and if we expand and do everything out, we get v is equal to 112 pi over pi. We'll do another together. And then I'll leave a couple for you guys to do on your own. So for number 7, we're going to find the volume of a solid obtained by rotating the region bounded by y equals x squared, the x-axis, and the line x equals 2 above the line y equals 6. So we're taking all of this and we're rotating it across all of this. So this is the whole space that will be rotated. So this line this equation is y equals x squared. Our washers are perpendicular to the x-axis, so x is the variable. Okay, so then our big R is equal to just that space from the x-axis to y equals 6. So our big R is equal to just 6. Our little r is equal to that 6 minus this space. So our little r is 6 minus x squared. So we have big R is equal to 6, little r is equal to 6 minus x squared. So then the area of our washer is equal to pi big R squared minus pi little r squared, which is pi 6 squared minus pi 6 minus x squared squared. which is equal to 36 pi minus pi times 36 minus 12x squared plus x to the 4th. Which is just equal to negative 12 pi x squared. Positive 12 x squared minus pi x to the 4th. So then our volume is equal to the integral from 0 to 2, since we're looking at x, of the area x dx, which is integral from 0 to 2 of 12 pi x squared minus pi x to the 4th dx. And when we do all of that out, we get 128 over 5 pi. Okay. So for the next three problems, 8, 9, and 10, it's all a matter of figuring out what your big R and your little r are, and whether or not you're in terms of x or in terms of y. Okay, so I'm going to leave those three problems for you all to do on your own as practice before we get back together next week. So that ends the video for part 2. People look out for part 3.